Hi, my name is Samuel Pacheco. In this discussion, I'll be presenting information on the change of gross domestic product, or GDP, in the U.S. between the years of 1929 and 38. This is an era of turmoil in the U.S. It's referred to as the Great Depression. This is because there were recessions occurring which negatively affected the GDP of the U.S. I will also be presenting on the total cost and average total costs of a company that produces surfboards. First, I will demonstrate a graph we will be referring to in the first part of our discussion. This graph represents the y-axis, this represents the GDP. The y-axis here represents the GDP of the U.S. in billions, and the x-axis represents the changing years. It's the change of years. So each line will represent a change of year. We have 9 points along our graph which represent the GDP on the specific year. However, we are only provided with 6 of the specific profits for specific years, so some of the data points will not be represented by certain GDP. They will only be points to refer to in our graph here. They won't be represented in our slope or in our piecewise functions. As we look at the graph, we can see that between the years of 1929 and 1932, there is a negative linear line that represents our first piece of the piecewise. Now we have to define the function for the piecewise, and we're going to do that by first finding the slope. We are also provided with a y-intercept here, which will help us in our calculations. But first, to find the slope, we have to use the formula m equals y2 minus y1 divided by x2 minus x1. It's also referred to as m equals the change of y divided by the change of x. So let's do 1, m equals y2 minus y1 divided by x2 minus x1. We could refer to our graph for the specific data points. We're provided with our y1 and our x1 and our y2 and our x2. So let's write that down. Our y2 will be referred to as 750. Our y1 will be referred to as 1050, and our x2 is 3. Our x1 is 0, because that's our y-intercept. So we're going to get calculation of negative 300 divided by 3, which also equals negative 100. So slope equals negative 100. Now that we have that calculated, we can find our information here of the slope-intercept form to find the function. We use our y-intercept 1050 and we plug it into the slope-intercept formula, y equals mx plus b. So slope-intercept formula, y equals mx plus b. This is an easy function because b is provided as our y-intercept, which is 1050, and we already calculated for our m, our slope, which is negative 100. So we will find that our formula equals y equals negative 100 x plus 1050, and that's the first piece of our piecewise function. Now let's move over to point 2. Point 2, we're going to calculate between this year here, which is referred to as 3 and 6. So over this change, we have a positive linear function. We're going to calculate the slope of the positive linear function. However, we are not provided a y-intercept, so therefore we have to do a different form of calculation, and to do so, first we're going to have to find the slope of the function. Now to find the slope of the second function, we're going to have to use the points given. And we're also going to refer to the same slope formula, m equals change of y divided by the change of x, y2 minus y1 divided by x2 minus x1. So we are given our data points here as y2 being 1000. Subtract that by y1 being 750, and we're going to divide that by our x2, which is equal to 6, and our x1, which is equal to 3. We're going to get 250 divided by 3, and this is going to be a weird function because it's going to be an odd number, but we're going to get 83.3 repeated. M equals 83.3 repeated. So we're going to use the similar function here to find our formula. We're going to get we're going to get the formula here, which is y minus y1 equals, I believe it's a divided by x minus h plus k squared. And then this y is going to be, we can plug in the formula for the information, but we can also just make it easy. Minus 750 equals 83.3 repeated. X minus 3, it's also going to be calculated as y equals 83.3 repeated, x plus 500, and that will be 2. That will be the second piece of our piecewise function. Okay. Now we're going to move on to the third piece, and the third piece of this function is an interesting part because it is nonlinear. This nonlinear function is going to be referred to, well, it's a parabola. As we can see here, it's not linear, not only because it's not a straight line, because we can clearly see the movement here as a parabola. It slopes there and returns us here. So we're going to calculate the parabola, and in order to do so, thankfully we're provided with the vertex. The vertex of the parabola is the point here, 7, 1100. So now that we have the vertex, we're going to use some formulas to calculate this. So the formula to calculate the parabola is going to be written as, should have put a dot there, equals a x minus h squared plus k. So h is equal to our x and k is equal to our y. Therefore, the formula is equal to y equals a x minus 7 squared plus 1100. So we plug in the next point provided on the graph to finish calculating. So the next point there is going to be 8, 1000. So here's our 8. So x is equal to 8 and y is equal to 1000. So now that we have our y and our x provided here, we can fill out the formula, which is going to look a little like this. 1000 equals a 8 minus 7 squared plus 1100. Almost forgot that the first time. So 1000 equals a plus 1100. A is equal to negative 100. Now we just plug that back into the formula. We get y equals negative 100 x minus 7 squared plus 1100, and that is going to be 3 of our piecewise function. Now we move on to the last point, which is another linear function. It's given here as our 2 data points are provided. It is also a straight line, and we can calculate the function by using the similar functions as the first and the second piece of our piecewise. So let's go ahead and do that. We have m equals y to change of y divided by change of x. Let's just use our information given. Slowly calculate. Our slope is equal to 350. Now we plug that back into the information here. 1, 2, 3. X minus 8. And then we get our function, which is 350. X minus, I believe it to be 1800. I might have skipped over some small things there, but that's our fourth function. Now that we have the fourth piece of our piecewise function, we can now devise our total piecewise function. So this is my favorite part because it's, in my opinion, the easiest. I'm gonna have to do this at a weird angle, but let's do that function. Boom. Okay, and now we have our first function, which is going to be y equals negative 100 x plus 1050. And our second function, I don't think I need to include the y equals. Yeah, no, I don't. So we're going to do that for our first function. Our second function is going to be 83.3 repeated x plus 500. Third function will be our parabola, which is negative 100 x minus 7 squared plus 1100. And our fourth function is going to be y equals 300. Oh my god, again. Y equals 350 x minus 1800. Now we're done with the functions of our piecewise function, but we also have to determine the domains. The domains will be easy to determine because we're given the data points, and since they are included in our function, every data point is going to include less than or equal to signs. That's because if we were plugging one of the x-intercepts into our functions, like 0 or 3, they will be calculable and referred to in our graph. So if we can make it easy, we can just refer to the sort of points of our graph here to determine the domain. So our first point of the graph is going to be 0 is less than or equal to x. Second point of the graph is going to start at 3, and we're going to have that. That's going to end at 6, and then we have 6 beginning here, greater than or equal to 8. And then lastly, but not leastly, x and 9, and that will be our domain. Each function refers to the properties between the linear line here for the first and second. So 1, 2, and then the third piecewise will refer to the parabola here, and then the fourth piece of the piecewise will refer to the last 2 data points provided, and our domain is provided right here as well. And that should cover the first section of our discussion, which refers to the change of the gross domestic product of the U.S. between the years of 1929 and 1938. Now that we have that covered, we can do our second topic of discussion, which is going to be our graph provided here. This graph shows the function of the average total cost per surfboard for an output of X surfboards for company. So average total cost, and X refers to the output of surfboards for a company. So the fixed cost of the company can be considered to be a lease payment on the necessary machinery required to manufacture the boards. Considering the price of equipment needed, companies often lease the expensive technology required, so that, of course, that's going to be necessary to provide output for the boards. You need to actually build the boards, and to do so you require machinery, which can be costly, so the lease payments are going to be non-variable. And to move over to a variable cost of manufacturing the surfboards, I work in sales. I would consider sales commission to be a variable cost, because commission structures are typically flexible to the total amount of sales by an associate divided by the amount of hours worked, therefore variable. We are given a graph. I'll refer to the graph again. We're given a graph that represents the average total costs per surfboard for an output of X surfboards for a company. The average total cost implies the cost of manufacturing per unit. This is opposed to the total cost, which is the cost of production for quantity of output. In summary, the total cost is the fixed cost and variable cost considers. So it's the fixed cost plus the variable cost. And the average cost is the total cost divided by the quantity of output. Mathematical expression to refer to the statement, which is limit of the average total cost function, ATC, as production increases significantly, can be written as, I'll write it down here, lim quantity approaches infinity, ATC times Q, which can also be stated as limit x, x refers to as Q, but Q approaches infinity, average total costs times the quantity. So that we can refer to as the limit of our function as the average total cost and quantity are calculated. As we observe the behavior of the graph given, we notice that the function decreases dramatically, and then it gradually approaches the limit here. We notice that the function never reaches the y equals 0 intercept, or the x-intercept, I could say. It also does not appear to increase at x equals 50, although it appears as though the graph indicated as production increases, the average total cost will be equal to 0. In reality, the graph is reaching a limit. It never approaches 0. The function of the graph will not reach the x-intercept, as the fixed cost must be factored into the equation, which I'm assuming is an asymptote somewhere here. I don't know if they calculated any fixed cost, but assumably a fixed cost would interrupt the approach to zero. It appears as though it asymptotically approaches y equals 0, as referred to as the asymptote that I was talking about earlier. It asymptotically approaches y equals 0, and it appears to be parallel to the x-axis. And as production increases and more surfboards are produced, the company achieves economies of scale because the average total cost decreases to a degree that infinitely approaches the limit. This is based on the data represented on the graph. That being said, if separate variable factors are to be considered, the scale may be disrupted, and the company may experience a decreasing return to scale. So yeah, if there were to be other factors considered, I think, maybe it'd have a decrease of sale as opposed to economies of scale. But that being said, thank you very much for listening. I hope you enjoyed this presentation, and goodbye.